Hi, I'm Roxanne Martin.
And I'm Emma Dowse.
I'm Michaela Bednars.
I'm Kyle Rudman, and this is the
Chi-squared Goodness of Fit. Chi-squared test for goodness of fit tests whether the observed distribution matches the expected distribution. The equation for this is the sum of the observed minus expected squared divided by the expected counts.
The conditions that must be satisfied in order to perform a chi-squared goodness of fit test are that the random condition must be satisfied, which states there should be a random sample or a randomized experiment from which you're drawing the data. The 10% condition states that the sample size of the sample must be less than 1/10 of the population in order to assure independence, and the large counts condition, which states that all expected counts must be at least 5.
The two hypotheses when performing a chi-squared goodness of fit test are the null hypothesis that the stated distribution of the categorical variable is distributed the exact same as the population distribution, and the alternative hypothesis is that the stated distribution does not match the population distribution. To illustrate the state plan do conclude process for a chi-squared goodness of fit test, we're going to do an example using the color distribution of NMMs. So here we're going to see the hypotheses for the M&M example. So our null hypothesis is going to be that all the colors, all 6 colors of NMMs, occur in the same proportions, and our alternative hypothesis is that the colors do not occur in the same proportion.
Now for the plan portion of the example, we will be performing a chi-squared goodness of fit test to prove/disprove the null hypothesis. To check our conditions, we're assuming that our sample comes from a random sample of M&Ms, and in that random sample there are 211 M&Ms, which is less than 10% of all M&Ms. Therefore, the 10% condition is satisfied. And for the large counts, all expected counts are at least 5. So if we divide our total amount of M&Ms divided by the number of colors equals 35, which is greater than 5.
Now for the do step, the easiest way to find the chi-squared statistic is to make a table. So we have the expected proportions for all 6 categories, and then multiplying that by the 211 M&Ms, we get 35.02 for each expected count. And now going through, we counted our sample of M&Ms, and we then, in our last column, found the chi-squared statistic. So we have the observed count minus the expected count squared divided by the expected count. And then we summed all of those values to get a final chi-squared statistic of 32.87.
Now for the do portion of the example, right off the bat we're going to calculate our degrees of freedom, which is 6 minus 1, that's the number of categories, minus 1. So we're going to get 5 for that. And then after we summed our chi-square statistic, we got our value to be 32.87. Then we're going to use that table of distributions of the chi-squared or chi-squared distributions, and matching the rows and columns, we're going to find our p-value to be less than 0.01.
So a more efficient way to do this entire process of calculating the chi-squared statistic and then finding the p-value is to just do it all in the calculator. So we can go to the stat button and go into edit and put in 2 lists. So in list 1, we're going to put the observed values, and in list 2, we put our expected values. And then coming back to stat, we can go to the tests and scroll down to the chi-squared test for goodness of fit. That's that GOF. And we select the L1, so list 1 for the observed values, and L2 for the expected values. And then if we go down and simply hit calculate, it does all of the work for us. So we see that that chi-squared statistic is the same as what we calculated before, the 32.7. And then we gives us an exact p-value. So we just said with the green sheet that it was below 0.01. So here it gives us an exact value that we see is almost 0. So this gave us all of the same thing, and now we can draw our conclusions from here.
Since our p-value is less than our alpha significance level of 0.05, we reject the null hypothesis. There is significant evidence to conclude that the colors of the M&Ms in the sample are distributed differently than how the colors of the M&Ms are distributed in the population.
Now that we've completed our example, let's go back and look at some common mistakes. So one big thing is that the expected counts here, it's 5, not 10. So in everything else, when we're doing the large counts condition, you have to have 10. But for chi-squared, you only need to have 5. And also, it's the expected counts, not the observed counts, so be sure not to confuse those two. As for the degrees of freedom, It is not the number of subjects minus 1, but it's the number of categories minus 1. So make sure that when you're going through it, you're counting the number of categories, not just the total number of items in the sample.
If you would like some extra practice problems, there's an FRQ from 2013, practice number 4.
We hoped you learned something new or refreshed your memory on chi-squared. Thank you for watching!